In this screencast, we'll take a look at how we can calculate the free energy and therefore the spontaneity of a particular reaction by using the standard reduction potentials. This first question says, using standard reduction potentials, determine whether the reactions are spontaneous under standard conditions. And we're given two reactions, and from this we need to find out whether it's spontaneous or not. So, two ways we can do this. First of all, we can find out from the voltage of the cell whether it turns out to be positive, and if it is, it's a spontaneous reaction in the forward direction. We can also calculate delta G, and if delta G turns out to be negative, that also means that it's spontaneous in the forward direction. And we'll look at calculating both of these in the next two problems. First, let's take a look at letter A. The way that reaction A is written is copper solid is going to copper plus 2. Therefore, it's being oxidized. It's our oxidation reaction, and therefore it's our anode. We also have hydrogen being reduced to H2, and this would be defined as our cathode. If we wanted to find the voltage of the cell, E sub cell would equal the standard reduction potential of our cathode minus the standard reduction potential of our anode. To symbolize that it's at standard conditions, we put a little circle right here above each one of the E's, meaning that it's at 25 degrees Celsius, 1 atmosphere pressure in a 1 molar solution. So plugging the numbers in for this, if we look up copper on our standard reduction potential tables, you can see copper's right here. It has a voltage of 0.34. And then if you look right down here, hydrogen is assigned a standard reduction potential of 0 volts. Remember, everything's defined based on the standard hydrogen electrode, also known as a sheet. Well, if we put these numbers in, you can see that the cathode right here we have defined as 0 because it's our hydrogen electrode, and our anode would be the copper, which is a 0.34 volts that we got off of the standard reduction potential table. When I calculate this, 0 minus 0.34 turns out to be negative 0.34. Well, we turn out to have a negative 0.34 volts for this particular reaction. And automatically that can tell us, hey, it's a non-spontaneous cell, or it's a non-spontaneous reaction. We could take this number and put it into our equation for calculating delta G and also see that delta G turns out to be positive. We'll do that in just a second. Let's look at the second reaction right here. In letter B, we have a different type of reaction going on. We've got Cl2 going to Cl minus, and so you can see that chlorine at a 0 adds an electron. Reduction is the gain of electrons, so that's our reduced portion of our electrochemical cell. And this will be defined as our cathode. And we also have 2I minus going to I2 with a 0, and so we can see that that's losing an electron. That's our oxidation, and this will be our anode. Okay, if we look up the cell potentials or the standard reduction potentials for each of these, we would do cathode minus anode. And if you find chlorine in here, chlorine has a value of right here, 1.36. And if you find the anode for iodine is, I believe, 0.53 or so. And iodine is down here a little bit further, 0.53. So we'll put those into our equation. And to find the cell, then, we'd have cathode minus anode, and our cathode is 1.36, and our anode is 0.53. Cathode minus anode would give us a positive, approximately positive 0.8 volts. And the important part is that it turns out positive, and therefore, yes, it is a spontaneous reaction. We can take that and put that into our equation for delta G, and we can find out that, yes, it would also give us a negative delta G. And we'll see that in our next question in just a minute. Well, our next question asks, which is the stronger reducing agent, mercury liquid or lead solid? And the terminology here is the thing to get over. Look at the words reducing agent. If something is a reducing agent, that's causing something to be reduced. that means it itself is being oxidized. So what we want to find is which one of these is most easily oxidized. And to find out which one is most easily oxidized, we can look at the table of standard reduction potentials. And remember from our table of standard reduction potentials, things up here are easily reduced, things down here are easily oxidized. So let's find out where these two are on the table of standard reduction potentials, mercury and lead. Mercury is right up here where it has a standard reduction potential of 0.79. Okay, 0.79. And lead is right down here at negative 0.13. Negative 0.13. Okay, 0.79 and negative 0.13. Well, remember we said the one that's the most negative is the one that's most easily oxidized. And that's what we want to know, so which one's most easily oxidized. And so we say that lead is the best reducing agent in this particular problem. Next question says, calculate the free energy change, and the equilibrium constant K at 298 degrees Celsius for this silver reaction right here. Well, the two equations we're going to look at is to find out the G, or the free energy change. And to find that, it's equal to negative NFE. N means the number of electrons that are transferred in the reaction. F is the Faraday constant, which is 96,500. And the units on that are coulombs per mole. It's the amount of charge per mole, because there are 96,500 coulombs of charge in a mole of electrons. And then E, of course, is our cell potential, or our EMF of the cell. So to find this, what we need to know is the EMF of the cell. We can write the half reaction and find out how many electrons are transferred, and plunk these into our equation. And don't forget there's a negative sign right here, which means that if the EMF is positive, the delta G will be negative, meaning that it's spontaneous. That's why a positive EMF tells you it's a spontaneous reaction, just like a negative sign for delta G does as well. So looking at our reaction here, we have silver, 4 silvers as a matter of fact, going to 4 Ag plus and 4 electrons. And this is oxidation because we're losing electrons, and this would be our anode. Remember, anode always starts with a vowel, just like oxidation. Then our other reaction actually has 4 electrons with it, and it has the oxygen, and we have 4 H pluses along with that, and it goes to 2 H2Os. And this is the reduction now of oxygen from 0 to -2. So reduction, remember, is our cathode, red cat. That's how you can remember which one's anode and which one's cathode. If we look up the standard reduction potentials for these, the E for silver is 0.8, and the E standard reduction potential, I'll put a little circle up here so we know it's standard, is 1.23. So if we do our calculation now, E of the cell is equal to cathode, 1.23, minus the anode, 0.8. And if you do that calculation, I think we're going to end up with about, 0.43 or so. Is that right? Pretty close anyway. 0.43 volts. Now we can take this number and we can put it in for the EMF of the cell. So delta G is equal to negative N. It's the number of electrons transferred. 4 in this case. Notice the balanced half reactions have 4 electrons transferred, times our Faraday constant, which is 96,500 coulombs per mole. And if you forget the Faraday constant, it's not a big deal. You can just look on here on the equation sheet, and they always have the Faraday constant listed. If you look right down here in this corner, I'll zoom in just a little bit, you can see there's the Faraday constant. They write it as a nice fancy F. 96,500 coulombs per mole of electron. Faraday's constant. Okay, zooming back out. Let's see, that's the Faraday constant, and then we need our voltage, which is 0.43 volts. And if you put those together, you're going to end up with a negative number that's, well, fairly big. And we know that that's fairly traditional or fairly common for a redox reaction, is that it has a large negative G, meaning that it's fairly spontaneous, or quite spontaneous, as a matter of fact.